In terms of large scale, it's the same. You have your rock characterization, you have your pattern, and you can adapt the explosive density. Here we can see how we have adapted explosive density in order to obtain the scope fragmentation. This is predicted that this is measured fragmentation. And also, in this case, we were analyzing also the digging results, the digging rates. Okay, so this is an example how to combine all these technologies. But since we are here talking about this project, and this project is allowing us to bring this technology into the quarries world, into the automatization of the quarry world. Okay, through this the project, the DigiEcoQuarry project, we are applying, or we are combining, or we are applying this technology into a quarry. We are reducing the amount of the truck, the holes, the system, and everything in order to be applied for the quarry, with two main goals. First, to have a control of the freight rocks, both from the rock type and also from the phase or the geometry of your blast, and also to have a reduction, in this case, of fine material, or to optimize the performance of the blast to match with the KPIs of the client. And normally for quarry, you don't want fine material, so you are allowed to reduce this fine material. You may allow to improve the uniformity of your blast, and also to increase the material recovery. Okay. So for this project, we are now in the second blasting campaign, and we are applying this standard, this process, in order to design the blast and to apply the different technologies in combination with the UPM to try to optimize the blasting results as much as possible. So first we go with the design. We have our pattern design that we do it in combination with the mine, with the quarry, sorry, and with the UPM. And this pattern design is sent to the drills. So the drills are drilling according to the blasting design. Once we or UPM gets the information from the drills, they characterize the rock with the model that Jose was explaining before, and they will characterize the rock in terms of whether there is massive rock, the limestone, or whether there is a cavity or the clay. Okay, and according to this, what we are going to do is to adapt the explosive according to the rock characterization. Whether they will have to introduce a deck, that is the green color, in order to stop or to avoid the step explosive to go through the cave, or whether we have to reduce the density because there is a clay zone, so we don't have to use as much explosive as we needed. This is more or less, this is a blast that we were performing yesterday, and this was the design that we tried to apply in the blast. Okay, this was cap density of 1, cap density of 0.9, and this was cap density of 0.7, just to reduce the amount of energy in this side. According to the design, when you do the design, you start creating different sections with different explosives, and you apply this explosive with the cap density according to the cap density of the energy that you have to apply. Okay, you can manage, or you can generate your design by calculating, or by calculating the amount of kilos using an average design that you want in the section or along of the hole, or by saying, okay, I want to design according to the capabilities of my truck. My truck can pump a specific cap density or specific densities. I will design according to the capabilities of my truck. Okay, my truck can pump at density of 1, 0.9, or 0.7. I will do my design for my truck to be more accurate, as much accurate as possible. Also, before blasting, we do this simulation in order to ensure kind of the fly rock, that with the design we are ensuring fly rock and also vibration control, to try to not repeat any timing or in the timing of the holes. And from here, we go from the real, we send information to the blast center. This is our cloud, and from here we send it to the app in order to start measuring actual data on the field. And from here, from the app, or within the app, we send it to the truck. So the truck has the design and start pumping according to the design. If you have 3 different densities, they will pump with 3 different densities. If you have a deck, it will stop at the deck for the operator to have time to put the deck and then keep pumping. And then, well, it is very important. When you are pumping, you have a quality control of the cap density, that we can see here, to match with what we have designed. And if you are not matching or you are not reaching this cap density or this density, this target density, you have to vary the parameters of the track in order to be more accurate according to the design. And also to have a control of the stemming length that is a curve or a crafting or five rock on the top side of your blast. So finally, the information from the track goes to the cloud at the end, and with this information we have the theoretical design and the actual measurement, and with this we can reach or we can manage the QAQC analysis. Okay, so this is kind of the whole process in order to have a thorough control of your blast. And now we go again with Jose Angel to assess the blasting results.
Okay, so Juan has told us so many things you can do in design, blast design, how much flexibility you have with today's technologies, explosive technologies, and blast design codes. In any case, all that must be based on a good geometry base. So you must get hold of a good geometry base in order to build all these maps, all these etc. must be built on a good geometrical base. So yeah, now after blasting, how was the blast? I worked many years for the explosive industry, and then I've been many years at university and also in contact with the mining and the blasting sector. And oftentimes I've been amazed on how little assessment of the blasters and miners get. Purely an eye impression. Okay, fragmentation. Well, it was fair. It was good. What's that? Swelling, displacement. Well, it's swell. Well, not so bad. It's not so good. The blast kept a little bit tight. The displacement was, etc., etc. You go nowhere with that to improve your blast. You need, I will insist that at the end of my presentation, you need to measure things. You need to measure things to control what you're doing, okay? And to reach a certain point. So I've included here 3 interesting issues of blast results: fragmentation, muck pile characterization, and eventually backbreak, if that interests you. Yeah. And we go again with, okay, let's start with fragmentation. We go again with, we take our little toy, the drone. We fly it now, a post-blast flight. We fly it over the muck pile, see what happens. Drones are nowadays inexpensive equipment. I'm not selling drones, of course. but look, when you get used to that, and initially we've been using different surveying, LIDAR equipment, etc., to get these laser profiling systems, etc. But some years ago, when drones blasted, so to say, and the application of drones was everywhere, we started using drones. And I can tell you that we can't live today without drones. And it's an expensive equipment. You can get a very good drone for these purposes that I'm talking about at less than €1,000. It may be a lot of money for my pocket, of course. I don't have €1,000 in my pocket here, but look, for an operation, it's not a big money. Even a small quarry, €1,000 is not a big money. Then you need to train a pilot. some of your engineers or some of your foremen, some people needs to be a drone pilot so that he or she can do the job. That's also inexpensive. It takes like a couple of months training in the afternoons. You can do most of that online. And it's like 100, 200 euro, the drone pilot course. So in the end, the flight itself and the preparation can take like 1 hour of this person. And then another hour computer work, etc. So it's not a big deal. When I'm showing all these about drones, etc., of course, big operations know that very well, but sometimes small operations, if some of you are connected with smaller operations, small mines, quarries, etc., say, look, I have a bad time in paying my payroll at the end of the month. I can't go into very much of this technologies. Too much. It's money. Look, it's not money, and the savings and the benefits you can get are many times fold what you spend. So we take our toy again, our drone, and fly over the magpie. Okay, and if we want to see the fragmentation, there are fragmentation analysis code, image analysis codes, segmentation codes that can determine the size distribution of your magpie. And with that, you can build a size distribution. Look, this is very complex. I'm showing here in a slide something that I can tell you is complicated to do it well. Because there is a number of errors that are waiting for you when you do the size distribution analysis here. Many errors, and you will run into them. You can't avoid them. Some of them are physical. It's impossible to get a good and exact fragment size distribution similar to the one you will get by sieving. Impossible. But you can go around some of the errors, and if you can get some fragmentation data elsewhere, for instance, in the plant, then you can come to a reasonably good fragment size distribution curve from your blast. And the way we're doing it, and this is the last I will tell about this, because we could have a seminar, and maybe we could organize a seminar sometime on fragmentation by blasting measurements, on all the problematic of that, and all the correction, etc. And we could do that. Of course, it's being more and more done everywhere. There's a lot of publications. I receive every week 1 or 2 invitations to review papers on fragmentation by blasting measurements on magpie, etc. There's a lot of work on that. Some of the work is good, is reasonable. Some of the work makes nonsense. But there's a lot of work being done on this. What we've been doing is to catch up a strong point, by measuring the fragmentation at the plant, at the processing plant feed, where quarries typically have a bypass grizzly, etc. And you can get that point. Then this is what you typically measure in your flight, and this is the real one. Like, going from this to that requires some process. And without, you don't get X50, or like you get X anything. You get all the fragmentation. Okay. More about magpie part characterization. You want fragment size distribution. It is important. For your mucking productivity, for your bucket fill factors, for your truck loading factors, for your energy consumption in the primary crusher. It's very important. Fragmentation is very important. But you may also want to assess how your magpie was. And I'm giving you here 2 examples. I think this is not seen on the remote. You have 2 examples here. These 2 examples belong to the quarry we're working with, which is, like I said, a limestone quarry. And you see, you see here that was the blast was basically there. And okay, you see here a normal thrown pile. Okay, whereas here you see a mud pile that half of it, large part of it, section of it, is very little displaced. Not because the blast was not well done, but because this quarry wants sometimes to blast like that with a very low specific consumption, very low powder factor, so that you just get some pre-fragmentation and just a little displacement. Because the rock is not strong, then the excavator can take it. Okay, so less money for the explosive supplier, low powder factor, but you're not bound by your explosive supplier. You're bound by your operational input. Sometimes your operational input will tell you to use more explosive. Good for these guys. Sometimes it will tell you to use less explosive. Not so good for this guy. But keep the customer satisfied, so they will be happy anyway. I was 10 years in the explosive industry, man. I've been on the other side of it. I was a cook, then I'm eating. So, look, how was your blast? How was your mud pile? Yeah, good displacement, little displacement, not much displacement. Oh man, you have your flight and you can give numbers to this. For instance, because these are, you see, this is not a photograph. You see all these like photographs. No photographs. It's an image, photograph like, but there's no photograph. This is really a model. You have every single centimeter here. You have the exact coordinate. You have the exact coordinate. You can do anything here. You can fit planes. You can adjust planes to this and calculate the inclination. We call that the repose angle of the mud pile. And you do that an insane amount of times, and you build a distribution of this. And you build a distribution of the angular repose. So you know that this mud pile has a 20 something in the range of 20 degrees angular repose. In this case, well, some of the blast was thrown, the fragments were thrown, some of it were hold tight close to the rock. How much of it? Okay, you have this bimodal size distribution. You have the normal angular repose here, and then you have large high angles that correspond to this. Okay, because these angles of this part of the micro, of course, they are much higher. But you also can calculate the volume of the mud pile and compare it to the volume of the block, and then you have these swell factors: volume of the mud pile to the volume of the block, the original volume of the block, and you can have a figure for the average, like you calculate. You calculate the center of gravity of this mud pile and the center of gravity of that mud pile, and you measure the distance of that center of gravity to the center of gravity of the block, and then you have the average throw. This is what you call the throw. And for the left, the throw was very, very little. It was in the vectorial number 2, somewhat in excess of 2. And in the other case, in this one, it was something close to 6. By the way, there were those two blasts were done with the same pattern, same drill hole pattern. This was done with a higher density explosive, so more explosive, higher powder factor than this one. Okay, same drill pattern. That's very good to have the same drill pattern, that you don't mess your driller too much, changing a boss. You're always changing me the drilling pattern. Sometimes you may need to drill 5 times 6 meters, sometimes 5.5 times 6.5 meter. I thought you want me to drill this in 6.5, 5.5. No, it doesn't matter. You always drill the same. Just use different energy of the explosive. You can get different results. You want that? Low density, less powder factor. You want that? Higher density, higher powder factor. Easy control. Mud pile displacement. And you get figures, you get numbers, you get numbers. You won't be able visually to recognize a throw from 5.86 to 5.0 maybe, but it's nearly a meter. You will recognize it like this. Okay, more you can measure. Of course, you see these profiles, the green is the original high wall, the original free face, and the red is the mud pile surface. You can see, for instance, see in this blast hole, very large burden. It didn't displace. See this one, less burden. It displaced a lot. Okay, you can use this to figure out how this is a result of the blast. The blast has already been blasted, so nothing to control here a priori. But it tells you a lot of how the blast, how the burden can vary your displacement. You may even want to reduce or increase your burden by looking at this. And you see these profiles. You can take these profiles like here. You see here the centers of gravity of these slice of the blast. Okay, no displacement virtually, some displacement. Okay, little displacement also here. You can, I mean, you learn a lot from these profiles. You are interested in damage to the slope. You can also look at the damage. Look at the back break. You see, this is with this post blast pipe. You have an incredible. You see, I told you how in the millimeter. So it's not a photo. Like I said, you can zoom into it, and you're looking into the details, and with that you can mark the back break. You can see here there's been a lot of back break. The distance from the closer holes is large. Chances are that the displacement in the blast was not good. So when those holes detonated, they were highly confined, and then they did a lot of gassing out backwards, something like that. I mean, I'm not going to analyze that at this point. We would need all the information for that. Whereas here, back break is very, very close to where the holes were. So little back break here, big back break here. You should analyze what happened here, what happened here. This is a post-blast, a post-mortem analysis, a forensic analysis of the blast. You can see what happened, and of course you will learn a lot how to design your blasts. Okay, the ultimate goal is to improve the performance of your operation. We are blasters. We've been even you, Juan, very short life so far. You're a young guy, but most of your life, he was my PhD student. Finished his doctoral work some years ago, and then these intelligent people by Maxam hired him. And but still, some years already on this. Myself, many years on that, and. We're blasters. Okay, we're blasters. And we focus on blasting, and we're specialists in blasting. We know about explosives, or fragmentation, this and that, etc. But you don't care about blasting. You don't care about fragmentation. You care about your operation in the end. Your ultimate goal is not do an optimum blast. Is getting an optimum of your operation. Okay. So you have to trim your blast. You need to do blasting, of course. You need to trim it for an improved overall performance. And this is for all the audience that is acquainted with explosives. This is what we call the mine to mill or the drill to mill concept. Okay, we start with the drilling and blasting. We are upstream of the operation, and then we launch everything downstream. Of course, it's not important per se how we do the blast, but the important is the whole operation, and you, as a miner, as a quarry owner, you want to have an optimum operation. The optimal operation may be close to the blast, or maybe away downstream from the blast. in any case, identify your KPI, your key performance indicators. Get data of the whole operation, not only of the blast, but also other parts of the operation, especially in the plant, in the crushing, and if in the classification plant, and also if it's a mine with processing more complex processing plant with grades, etc., etc. Get get data of the whole operation, and then what you have to do is to align those data that you are getting from the plant, some fraction amount, some yield data for metallic mines. All that, try to align that you are measuring on a timely basis, every day, every week. You need to align that with your blast, because what you want is to make a blast, check out how the whole operation is, and then go back to your blast, change your blast, see how your KPI move, and do that until you are trimming the system for an optimum overall percentage. Align blasting data with downstream. Normally, downstream are plant. You could also have some KPI that are not really in the plant. For instance, maybe your mucking efficiency, how fast you muck, you load, you dig and load your muck pile, and you haul it to the plant. Okay, this could also be a KPI. What's the bucket fill factor? How many? What's the time that I need for how many passes of the excavator do I need for the truck to fill up? Things like that could be KPI. But normally they are down in the plant, because this is closer to your production and to your sales material. Of course, understand what you do, and normally, of course, any miner or any quarry owner will do that. This has to be done. Understand and filter data variability due to rock mass changes. Sometimes you think that you are blasting differently, and it is the rock that is, and you think often, well, what's happening here? Is it the explosive? Was it the drill? Was it the drill pattern, etc.? No, there's sometimes it's just that the rock changes, and for that it's very interesting to have a good rock mass control, like I was explaining in my first talk. But sometimes things like weather and other non-controllable influences are important. If you have more water in your material, then the plant may behave differently, etc., etc. So that has to be understood. Okay, so identify KPI. This was an exercise we did at our pilot operation, CEMEX operation in the vicinity of the grid. This is the KPI that we identified in discussion with the quarry, some fractions, working time, different working times. Some of them you want high working time, small working time, some operations, small reject, high. Okay, these are KPI. You have to align those KPI. Okay, those KPI are usually measured on an hourly basis. They are mass flow measured from belt scales, belt weighs. You get the mass flows, etc. And if in principle you may not know where or what blast was that material originating from. So one of the talks in this series of the DigiEcoQuarry project was the hauling tracking system, the truck tracking system, and we've been using that, for instance, to assign material that was being loaded into the plant with a certain blast, because not blasting and then loading into the plant is not linear every time. And it's not that you blast and then you load and all your trucks go to the crusher. Sometimes you have intermediate storage points where you leave their material. Qualities, you may have different stockpiles for mixing qualities of the different rocks. In this case, rock with higher amount of clay, with rock with more pure limestone, maybe mixed for giving a consistent amount of clay, etc., etc. So you may have several stockpiles here that then are put into the crusher, into the plant. So how can you say if that material that you are loading and with those KPI in the plant came from a certain blast? That's difficult. That's difficult. The tracking of the material is in quarries and mines very difficult. Imagine those mines, metallic mines that have big stockpiles that do heap leaching over there. Okay, or intermediate, any type of intermediate stockpiles. So that's difficult. This is an example that we are very proud of, where we started looking at that and looking at data that the quarry was providing us from the plant, from their normal procedure, and of course they know how much material they are feeding, and we were comparing that material from the quarry data, from the plant data. We're comparing that with this truck tracking system. By the way, the truck tracking system, this is the green, is the blast. These are the blast codes, the colors, and this is points where, because a GPS system was mounted on the trucks of this quarry, so we knew when when the trucks were being loaded and when the trucks were dumping. And from that, because we know exactly each of these points, we know the exact time that this truck is loading. Then if this truck is going directly to the plant, then we know that this material in the next hour or so is coming from this blast. Okay, so when we have a good span of time where we see that the material being loaded was coming from the trucks from this place, we know that the plant is operating on the blasts, on the material of this blast. And in the beginning, there were tremendous errors. This is the ratio of the truck tracking system calculation and the actual data provided by the plant. And you see that this ratio in some cases was nearly 0.1, 0, sometimes it was close, but there was an average mistake, an average error of 40%, when the ratio should be 1 for an excellent estimation, and the average was that. But if you look at the average, say, okay, 40%, it's big, but if you think on a day-per-day basis, well, that was really poor. So we managed to understand better what this tracking system was doing. Something was not being done properly, something they call the geofences, the area that this GPS was delivering data was not correct. A lot of the data were lost, etc. And by the end of this was September, by the end of the year, some of the guys that were involved in this are here. We managed to get a very good matching. So check data for consistency. Check data for consistency. Any new measurement you do, etc., think that it may be wrong. So don't believe it per se, and try to check for consistency. Try to reconcile it with other data. This is another exercise of reconciliation of volume of the block measured with our volume calculations from 3D model, so very accurate, and some mass loaded with a truck tracking system. Okay, they should be aligned here with this. This is our regression curve with the slope being the density of the road. Basically, it is the slope of this straight line is the density of the road. Okay, there's some dispersion, but still, we are relatively satisfied. Okay, some final and perhaps obvious tips by way of conclusion. We have explained here how Dr. Navarro and myself, how you can improve drilling and blasting by harnessing available technology. A large fraction of the improvement comes from having a better knowledge of the rock and a better control of the blast design variable. Rock, MWD, blast design, blast execution variables by using appropriate models. Blast design must be done with a good geometrical control. Blast design variables and blasting result might be assessed with numbers. It's something that I always say. Excuse my being a docent. I always speak like that. It's numbers. Numbers really mean something. If you don't have numbers, then you don't know it. There's a quotation by Lord Kelvin that says that if you want to know, if you want to describe something, no, if you want to know something about something, if you want to know anything about something, describe it with numbers. Give it a number, and then you are starting to know what it is. So if you want to keep track of your blast, of your operation, etc., use numbers. We have told you here a lot of ways of getting these blast design, blast results in terms of numbers. Data repositories and management systems may be of great help to store and analyze data. Now, I'm not going deep into that because there's been some presentations in this series of workshops about this project. The DigiEcoQuarry project is also developing this. The D of Digi is about trying to have a concept for a data lake, data repository where you can have anything over there so that you can pick here and there to make your analysis. Okay, this is the concept, idea. If no such thing is available, which happens to be the case very often, this is usually available also for big operations. Some of the slides Dr. Navarro was showing came from Escondida in Chile. Okay, Escondida is the biggest open pit mine, not in the world. There's big open pit mines in Europe, in northern Sweden, but Escondida is bigger. I see some Chilean folks over there. Okay, don't argue to that. We accept it. Big mines are in Chile. So yeah, they have excellent dispatching system and excellent databases where they have every single data, measurable drilling data, models, of course, drones, several drones, and expensive ones, I guess, and etc. Huh?
The cheap ones.
Okay, the cheap ones. We don't need
the expensive ones.
Yes, we don't need expensive one. It's just a photograph. We're just taking photographs. It's easy. So if no such thing is available, which happens to be the case in many smaller operations, try and get your data. Devote 1 hour after each blast or to gather from time to time to gather those data, write them in Excel spreadsheets. Be thorough with the data. In some time, you will be able to visualize data, see relations between variables, and understand trends and look for optimums. In of course, this data repository or your Excel files should also include economic parameters. We haven't gone into that, but of course, all of this boils down into economy. Also, you need to know what's your prices, what your optimum is for you your optimum point is that maybe it's the highest profit, maybe it's the highest revenue. Okay, depends on your operation on the time. So I look for optimum points. And if we have helped you a little bit for that with this presentation, then we are extremely happy. So that's it for today. Thank you. This was a joint effort by Maxam Technical Services and Exploration Blasting Lab at Technical University of Madrid, with the collaboration of CEMEX that we gratefully acknowledge here. It's one of their operations in which we are doing the work. And of course, this is all being funded by the European Union's DigiEcoQuarry project, a Horizon 2020 project. So that's it. Questions? Yes, do we have questions?
Yeah, too.
Okay. Questions? Okay, questions by an anonymous attendee. Could you please explain again the difference between natural air cuts? Okay, that's yours, Juan.
Yeah. Question is, could you please explain again the difference between natural air cutting and gas compressive air system? How exactly is air introduced in this process with natural air cutting? Okay, with natural air cutting, at the end, the matrix go to the pump, and the pump has a kind of an endless screw. Okay, the endless screw is rotating. Or the faster it rotates, the more air bubbles is catching the explosive inside of the pumping when it is pumping. Okay, so this is more the basic. It has more complexity than that, but just to understand how the matrix, how the explosive gets the air. And with the gas system, you have at the end of the hole, you have the different system with different capillarities, one of these capillaries has the additive, the other one has the air that is connected to the air compressive, with an air compressive system, and with automatically you can change the amount of air that you are introducing into the capillary, and all this mixture is happening at the end of the hose. So the more air, the lower density, and the opposite. Okay. Okay, and the second question.
You take the second thing.
Okay. You introduced so many technologies during this workshop. When there are no doubts that there or can be possibly contribute to optimization of drill and blast, don't you think that it could be overkill for a small quarry operation?
Okay, go. Go. See what you think.
No, I mean, at the end, it is depending of how big, how large, how small is the quarry operation, or how profitable can be to apply all these different technologies into the operation. If you have serious problems and you need a thorough or significant change into your blast, you may go to the technical point of view and installing different technologies. If your blast is going well, maybe the positive impact that this technology can apply into your operation is not as significant as it could expect. Okay, from my point of view, every technological deployment to any operation could add a significant value, or could gain value into the operation, to the total cost of the operation. But it's depending on every quarry, every operation has to do their numbers. Technology is there to help you with any difficulty. Services are there to help you with any difficulties. But at the end, every technology will serve better depending on the operation. I don't know if you want to add something to something.
Yeah, I agree at all with you, Juan. Of course, if you're a small operation, you don't have so much technical skills, maybe just the head or there's a few technical skills in the operation. it may be difficult to, of course, to put in place a lot of these technologies. But think of something. I think out of the people that is there, I don't know. I'm thinking of for instance one thing that you can very easily measure with this system. Of course, the system requires a drone flight. That's something that may look very complex, very complicated. It is not. Think of one of the variables, of the many variables that you have. Think about the burden of the first row. Think about the burden of the first row. You have to control that burden. If you don't control that burden, then you may run into problems, into safety problems. You may have fly roll. Sometimes you may have wild fly roll. I don't know where this question comes from, but for instance, in the UK, since many years, since at least 15 years that I know, you must have a control of the burden by profiling, by doing what we used to call a laser profiling of the burden. And so you need to have some survey, some borehole survey, some borehole deviation survey, and laser profiling. Laser profiling is like LIDAR nowadays. That was laser profiling was the technology used. We have a station, an MDL station, laser profiler, and we bought like by that time, 10, 15 years ago. And you need to do that by law. By law, you need to control your burden because of safety. Just because of safety, not because your blast will be better or worse, or your fragmentation will be better or worse, just for safety. Well, nowadays, you can do either. You can have a laser profiling system, a LIDAR system, that will cost in the range of 20 to 30,000 euro, maybe a little less if the definition is smaller. And then you need a borehole deviation probe. Okay, you still need a borehole deviation probe, but you can do that with you can do this surface profiling with the drone flight. The drone flight that you get the whole block, you have more than you get with just a flight. And the device that you need to do that is less expensive, and the time you need to do that is less. And I have just told you one thing. And of course, again, to this question, to this small operation, of course, you cannot get everything and you cannot do everything at a time. But at least we wanted to let you know what you have at your disposal. Depends on how close are you to your optimum, how many problems you have and you need to solve. What are your questions? Sometimes you can do this on your own. Sometimes you may hire this to a consultant. And that consultant will be able to use all these or some of these technologies. So it's not, of course, I'm not telling that any quarry should do everything that we've been doing, but we were just giving you an overview of what can be done with nowadays technology. Yes.
If I may, thank you very much, Professor and Doctor, for this informative and very valuable presentation. If I may ask for you to shed some few lines on the environmental impact for this vehicle. Definitely, you will give enough information about the safety and the security, and the efficiency that I do totally agree with what you mentioned lately, but we need to see more, to hear more about its environmental impact and sustainability.
Well, can I say? Doing things well always pays. If you do good, if you optimize your fragmentation, you will spend less money in your crushing plant. So you will be more energy efficient. You will be greener. Not all vibrations. Well, yes. Again, vibrations. That's also on the that's also in a way environmental, or at least social. You have a better control of vibrations, like Javier was saying, because you don't have you don't have unattended results, because you know well how your normally high vibrations comes from heavily confined holes, etc. With this, you may get away with that and have better vibrations.
If I may,
yeah, of course,
regarding the explosive and everything related to, for example, in terms of transportation on CO2 in the footprint, you are able to install your plant side of the mine. I mean, quarry is a bit difficult, but in a closed area, close to the quarry, you may reduce the transportation. You don't have to put all your truck or your manufacturing truck out in the road or in the public transport there inside of the mine. So you're reducing. Also, for example, depending on the explosives that you're using, you have different capabilities. One I was explaining was the crosslinker. You have an explosion that is crosslink that will not migrate through cracks, that is water resistant. At the end, you are reducing the migration, the ammonium nitrate liquids into the field, into some residual water could be filtrating into the soil. So you are helping to secure the environmental in this way. And also, for example, some explosives, some of the explosives I was talking about, like the water gel, can be when you're mixing up with when you are blending with AMPHO. Okay, any matrix or any both emulsion and water gel can be mixed up with ammonium nitrate with AMPHO in order to have a blending. So depending on the operation, you can increase the results. Okay. Normally, the AMPHO is a combination of ammonium nitrate plus diesel. Okay. With the real place, for example, you can change the diesel by waste oil. So waste oil coming from your machinery, you can recycle this waste oil, so you don't have to treat this waste oil. You will detonate it. So you are kind of saving, consuming less oil or less treatment, less waste oil into the environment, and also reducing the amount of diesel into your process. So it's an example. How can you improve? Okay.
Thank you very much.
Okay, I think we're done.
Thank you very much.
Well, this workshop has come to an end. First of all, I'd like to thank our two brilliant speakers of today. Thank you both. Also, thank you to all of you who attended here today, and also thank you to all of you which are at home and have been with us during all these weeks. Thank you.